I'd like to thank Gediminas for the invitation, and also it's great to come back to Europe. Um, some of you might know I spent 2 years in Innsbruck, but during the pandemic, I have not been able to kind of visit Europe for quite some time. It's good to see many familiar faces and also new friends. All right, so I'm happy to tell you about this what we've been working on in the past couple of years, and with a focus on this Bose-Einstein quantum chemistry. All right, I'm Cheng from University of Chicago. And let me see, that is this one. Okay, good. So at University of Chicago, we have been working on this quantum simulation based on co-atom molecules to study and address some of the fundamental issues in other fields. Okay, for instance, this in nuclear physics, field body problem. In cosmology, try to understand kind of some of these models in cosmology. Say one recent work is trying to simulate Hawking unroot radiation. In jet physics, we look at this also kind of flow case system, look at the jet formation and subject structures and pattern formation. Okay, but more recently, and probably more relevant to a lot of you thinking about quantum many-body system, trying to identify new form of quasi-particle. Say, very recent work on this fermion-mediated kind of phonons, and also kind of a topological defect, emerging property of this defect in this density-dependent gauge field. And also, a couple months ago, we published this paper, realized a kind of a twisted bilayer optical lattice, identify new type of superfluid phases. But today, I'll be more focused on the most recent work, trying to see this going from atom to molecules and see the dynamics of this kind of pairing, okay, in this quantum regime, in the what people call kind of superchemistry. Right. Okay, so talk about how do we go from ultra cold atom, ultra cold molecules, and what exciting physics, how exciting chemistry, okay, we're supposed to see, okay, and second talk about the experiment, okay, how do we form this molecular condensate, and see going from atomic condensate, molecular condensate, what kind of dynamics can kind of couple these two matter wave fields. All right. So many of you probably know quite well. This is a very exciting area. Okay, this trying to extend our tool set and this simulation capabilities. Okay, quantum technology from atom to molecules. Okay, and they want to see quantum effect. Want to go to lower temperature. Okay, so you can prepare a molecule in the one particular quantum state. You want to go to high density. Okay, so you can start to see many body effects. Okay, at the end of the day, there is you wish to go to the upper left corner and enter the so-called quantum degeneracy regime. Okay, and this has been a kind of goal in this community for a number of years. You can see very nice this review paper. Okay, shown here. All right. And this one of the work that this when I was in Innsbruck was trying to see how we can pair atoms into molecules. And at that time, we were able to kind of start with a kind of a condensate of cesium atoms. We can create almost 10%. We can pair about only just 10% of the atom into molecules. We never fully understood why the pairing is so bad, because supposedly these atoms are all in the lowest state. Oh, okay. So this. Okay, and then we convert about roughly 10% of the atom into molecules. You can see these are the atoms. And after we create a molecule, we can use Stern-Gerlach separation to separate these two species. That's in 2003. In the same year, a whole bunch of other these molecules be created, okay, based on atomic BEC, based on Fermi gas, as well and also later on, also based on Bose-Fermi mixture, the whole bunch of the huge list. And this list also kind of becomes a kind of foundation to explore new type of kind of reactions, state-to-state quantum chemistry, and new application quantum metrology and so on. Okay. All right. The molecule we created at that time, okay, was this using this particular phase bar resonance. This is the energy diagram for cesium atom in the low field from 0 to 30 Gauss. And the cesium pretty big and complicated. even within this small range of magnetic field, you can see that many molecular states. We can choose a particular molecular state to realize a kind of a state-specific reaction. Okay, atom in particular state coupled to molecule particular state. Okay, and we have a very good agreement with the theory calculation provided by these two gentlemen. All right, and then that's almost more than about 20, exactly 20 years ago. All right, and then the field started going to a slightly different direction. What we realized at that time is that these molecules can be created. They seem to be really, really cold, maybe even quantum degenerate. However, they are not stable. Okay, almost in all these experiments that created this molecule, they don't really last for too long. Okay, not enough to really see these condensate. And then people start to think, one of the reasons maybe these molecules are not really in the true ground state. If you go to the ground state, it might have higher probability to get the molecule to be stable. The more stable molecule, you can have a higher chance to condense them. Okay, and second, some of these molecules, some molecules are more interesting. Okay, if you start with a cesium, get a cesium-2, that's a kind of homonucleus molecule. There will be no dipole moment, but some molecules have a dipole moment. They maybe even can be have a more kind of a new knob to control the induce a long range interaction. Finally, people also saying this short range this molecule in the ground state, because the size of molecule is smaller. Okay, then it's more relevant to kind of the kind of quantum chemistry type of kind of experiment. It's better to use kind of ground state molecules. And the kind of molecule these people realized 20 years ago more about these phase bar molecules. They are very, very weakly bound. Because they are very weakly bound, people think they are not stable. Okay, and also because they're very weakly bound, the size is very large. Then typically you see such kind of large molecule with no dipole moment. Okay, and lastly, this very weakly bound molecule, people see that probably not chemically interesting. But today I'm going to tell you these are all wrong. Okay, turns out this phase bar molecule they're all wrong, but they can be collision stable. Okay, turns out they can also be very small. They can be chemically interesting. Okay, all right. Okay, so this is some kind of recent calculation on that specific molecular state we're able to condense. And this is to show my student working with Paul Julian to determine the molecular wave function. You can see this is a wave function, okay, and this is R, the interatomic separation of molecular state. Okay, the size of the molecules rough a bit below kind of 4 nanometer. Yes, 4 nano. Right, this is angstrom, 80 angstrom. Okay. Right, so it is, even though this very weak molecule, they are short ranged. Okay, they can be, there's higher chance that can also induce some interesting chemical reactions. Okay, all right. So then this, so about this couple years later. Okay, now we're talking about this in recent years, in 2018, 2019, these people can really get this. In Juzeliūnas group, they get a ground state molecule, rubidium potassium, into quantum degeneracy. This is fermionic, the degenerate Fermi gas molecules. Okay, that got the community very, very excited. Okay, we are now really enter the upper left corner in the quantum degeneracy regime. Okay, and just 2 years ago, we also showed that this molecule, this type is a phase bar molecule, the very weakly bound. Okay, something we studied 20 years ago, we failed to get the BEC. Finally, we found a couple tricks, okay, to get them also condensed. Okay, and we improved the efficiency from 10% to 20%. Okay, so this is a BEC of the atom, and this is a BEC of the molecules. Okay, all right. So what's so interesting about this type of molecular molecules? These molecules. First of all, the kind of the trick we figured out that have been waiting. I tried actually in the past 20 years. I tried so many different times. Eventually, there are two things that really help us to get these molecules stable. First of all, we realized that. Let me see. Can I go back? Yes. Okay. Let's use the first button. So we try to summarize the experiment almost in the past like 15, 16 years. Okay, people trying to go to lower and lower temperature. When I found 250 nanokelvin, 15 nanokelvin, 11 nanokelvin. Many molecules doing this 20 years, we try to start to realize If you go to very low temperature, then the inelastic collision is getting worse. The system becomes less stable. But that doesn't apply to all the molecule people have found. And these are a few particular molecules that we found. Okay, and it turns out this is a kind of loss coefficient from 250 nanokelvin, 53 nanokelvin, and finally for our kind of most recent experiment going down to this 11 nanokelvin. Okay, we see we have reduced the loss by almost this 1 order magnitude. Second, we found that if you try to reduce into the two-dimensional instead of the three-dimensional gas, you go to 2D. In 2D regime, you can still get BEC, but the confinement in the z direction is much stronger. Okay, it's quantum pressure limited, so we can get to we can reduce the loss even by another factor 3 to 4. Okay, at the end of the day, our molecule, even this very weakly bound molecule, has the same stability as Ju is this fermionic molecule in the ground state. Okay, so we have very similar kind of stability. So that's also the reason we can get this molecule to condense. All right, our experimental procedure is the following: we start with atomic BEC, and to get the two-dimensional kind of geometry, we made the dipole trap essentially like a circular box. Okay, all right. So uniform density inside, as you can see here, and the sample size is roughly about 20 micron across. Okay, and then we induce a so-called phase bar resonance. Okay, and then to couple this atom to a particular molecular state, and then we perform search on a couple candidates, identify the molecular state that are more stable than the others. So in this particular molecular state, the stability is better, is good. Okay, and then we pair some of them into molecules. And for those atoms that are not paired, we need to immediately blow them away. Okay, this atom molecule collision turns out to be pretty bad. Okay, so this can be done within a small fraction of a millisecond. So immediately after we pair them, we blow the atom we don't want away. And this is the image of the molecules. To see the molecule, what we do is we need to we prepare the molecule, blow the atoms away. To see the molecules, we can essentially dissociate the molecule back to two atoms and try to see the distribution of the atoms. Okay, that's why in most of the molecule image, okay, what I'm showing here is a 2nm, 2 times the molecule density, because what we see, we have 2 atoms out of 1 molecule. So this molecule, they form a condensate. Okay, we can determine the molecular scattering length. We can determine the kind of chemical potential, major chemical equation, the state, and so on. Okay, we can see this earlier measurement. We can either do time of flight or do the in situ. You can see a bimodal distribution. Okay, and we can get about nowadays maybe like 30-40% of condensate. Okay, and so the remaining kind of thermal gas molecules. All right, so that's about our system. So how do we try to see this reaction? What's a new kind of what's new physics? Okay, yeah, atomic BEC, the molecular BEC. So what's new here? All right, let's talk about a little bit about chemistry. I think chemistry, we know this from a kind of general chemistry textbook. Okay, typically how does chemistry happens? From collisions. Say 2 particles that collide, and it's a kind of find this cross section. The cross section that determines kind of the probability. Okay, this any collision can lead to a particular product. Okay, right. But in the many body regime, things can be very different, because now we have the BEC. That means all the atoms that occupy the same quantum state, they are doing exactly the same thing. When you create a molecule, this molecule also in the same state. And these are also bosons. So therefore, the reaction behave like a macroscopic matter wave. Okay. So to describe something like this, typically what you use is kind of use many body wave function, say in terms of second quantization form, and the interaction, or you can say reaction, can be described by the term like this: you have 2 atoms that collide, and that create molecules, or the other way around. 1 molecule can be dissociated into 2 atoms. Okay, so you can write down the kind of Heisenberg equation, write down this equation of state. equation of motion. Okay, then look at this equation. Immediately, just think about this kind of the differential equation. You know this differential equation is not trivial because it's nonlinear. When you have this kind of and the couple differential equation that's nonlinear, you're going to promise something that is have a very different kind of scaling law than the linear differential equation. That's what you learn in the kind of general chemistry textbook. Okay, and this nonlinearity comes about because you have a quantum state occupied by many particles. So the way atom go to molecule come back to atom would depend on the population itself. The more population you have, the faster this oscillation will be. Okay, this is the nonlinear wave mixing, just like how you say do high harmonic generation in nonlinear quantum optics. All right. So one of the main prediction is so-called kind of superchemistry. That is trying to say that because of macroscopic occupancy, okay, the reaction rate and this coherent process is going to depend on the population, okay, in a particular way given by the field equation. So let's see what would be the prediction. All right. So given this equation, it turns out. Okay, so just this particular equation. Turns out you can write down, you can try to solve it, and can write down some kind of this equation of motion. In some way, it looks very similar to kind of what we learned in mechanics. It's something like a kinetic energy term. It's how fast the molecule number is changing with time. And then another potential, what is kind of you can call this effective reaction potential. Okay, and the sum is a constant. Okay, but right here, Nm is a operator. Nm is operator. Okay, so with such insight, you can try to draw kind of this reaction potential like so. On one side is 100% atoms, the other side 100% molecules. And when you bring the system to phase bar resonance, that means atomic energy, molecular energy are identical. Okay, that's why they have the same energy here and here. However, okay, this potential provide additional minimum when they coupled. Okay, then the system can go to, okay, it can relax into some kind of equilibrium, okay, where there's a mixture between atom molecules. Okay, and this the process coherent. That means the system can also oscillate. Okay, near the bottom. Right, but remember, this is not the differential equation of a kind of a classical variable. This is a quantum field operator. Okay, so if you really try to solve it, say try to do exact diagonalization, if you start with 0% molecules but 1,000 atoms, then the molecule number can go from 0 to 500, but then very soon it becomes really complicated because the system can have all kind of complicated superposition in tangled states. If you try to evaluate the kind of expectation value, and then you see the molecule goes up and go down, it seems to be oscillating, but it looks like very quickly then it kind of you will kind of damps out. But there's no damping. In this calculation, in that diagonalization, there's no damping. Okay, it's just if you look at the expectation value, it looks like there's a damping, but the system just becomes really complicated because all the possible, the Hilbert space is very large. And this is similar to what we see. If you start with, in our experiment, we have this 20,000 atoms to begin with. Okay, and t equal to 0, we turn on the phase bar resonance and see how the molecule number increases with time. Okay, and then what we see is that the molecule number increase very quickly in the first few hundred microseconds, and then somehow gets stabilized. And then atom number also quickly reduces, and then after some time it also gets stabilized. And within the first 3 milliseconds, okay, the population pretty much remain more or less constant to within 10-20%, and showing this additional oscillation. Okay, it seems to be kind of two-step process. First is the very fast kind of a change with how we call the relaxation near something, some kind of equilibrium, and near the equilibrium there's some kind of oscillation we can see from both atoms and molecules. So if you analyze the first part of the process, to see how in the beginning how fast this atom decreases, molecule increases. Okay, and then we can make a plot on the right side. Okay, phase bar resonance is right at 0, and all the dots are our measurements. Okay, some measurement below the resonance, some measure above the resonance. You can see how much the phase bar resonance enhance this kind of reaction process. Okay, so if you cannot see clearly, the y-axis going from 10-second lifetime, 1 second, 100 millisecond, 10 millisecond, 1 millisecond, 100 microsecond, 10 microsecond. It changed by 6 order of magnitude. Okay, something that can stable for 10 seconds suddenly become only a few microseconds. Okay, in terms of this lifetime, it's totally crazy. Yeah, and what we see is that there's some kind of Lorentzian background. You can see the measurement on both sides. When far away from the resonance, it's pretty symmetric, and the Lorentzian fit pretty well. However, over this very large dynamic range, okay, we see some near the resonance, some very strong enhancement. Lorentzian is already kind of 1/Detuning square kind of enhancement, but this is something that goes even faster. If you look at the magenta line, okay, it shows that it increases as a detuning to the power of, I think, 5.5 to 6. It's really fast. Okay, when you see the data going multiple order magnitude, you see that you want to go back to you want to go back to the original data. Let's see the data how the things can change by many order of magnitude here. So you see, when you are far away from resonance, the system can stay for multiple seconds. So in this case, 700 milligauss away from the resonance, you stay after 1 second, you probably lose kind of 10-20%. And 74 milliseconds, you should have about 100 millisecond lifetime. But when you go to 30 milligauss, 28 milligauss, 19 and 9 milligauss, you see something qualitative different is happening right here. Okay, you see the population start going down, and then right here become very clear. It's a very fast kind of a drop, and then replaced by some kind of constant value. Okay, you can no longer fit this data with a single exponential like what we did. Okay, for very going far away from the resonance. Near resonance seems a very fast what we call relaxation, and after that maybe there's some oscillation, but pretty much a constant within the few milliseconds. Okay, so it's clear there are two-step process happening here. Okay. All right. So the second observation is that very soon after relaxation, we see this small oscillation, okay, on both atom molecules, and that oscillation turns out to be very sensitive function on the particle number in the system. Okay, so if we start with 5,000 atoms, 13,000 atoms, 30,000 atoms, you can see these oscillations are very quite different. If you try to perform an experiment starting from 5,000 and try to change the particle number and try to measure this how fast oscillation, the oscillation frequency, okay, then with this is you see our data. Now I first just show our data, and then this before I showing the fit. Okay, and based on these two body coupling model and together with harmonic trap geometry and so on. Okay, and this is a prediction. The prediction is a system described by this kind of this two body coupling. And this is a model everybody using in the literature before our experiment. And we look at this, yeah, it doesn't look good, right? Okay, so but that's the only theory that we had at the moment. Later, we are forced to think about other possibilities. So two-body process might not be doesn't seem to fit. How about I consider three-body? What with the hint from our data is that it seems to depend on atom number and with a much larger exponent. You try to fit the data, okay, with some kind of based on some kind of polynomial fit. The exponent is 0.7. Okay, but the three-body model, okay, three-body model is given by something like this, where what you see here is the three atom coming together, three atom in a condensate. Okay, think about it, three particles come together, and then two of them form of molecules, and then the third one remain in the form of atoms. Okay, you will say if you think about kind of general chemistry, you'll say this process is identical. It doesn't really matter how many come in. Your equivalent here, two atom convert into molecules. But in the quantum field, it matters. Okay, once you have more operator in your Hamiltonian, then the scaling law will be totally different. Okay, even though at the end you still have two atoms converted into one molecules, but the three-body prediction is totally different from two-body prediction. Okay, good. All right, so I'd like to summarize. Okay, so we look at this reaction between this atom molecule in a quantum degeneracy. Okay, and then we have we see the enhanced kind of a reaction as a function of the system size, and our measurement on these exponents seem to support the three-body process. Okay, and and we're currently doing some the coming experiment. Another kind of prediction for such kind of a reaction in the many-body regime is that in quantum mechanics, okay, the phase also matters. Okay, so the reaction in principle should also depend on the phase. In particular, that the phase determines whether oscillation is going up or going down. Right, so we're trying to, in principle, according to this field equation, we play with it. You will suggest that there should be a many-body phase for the molecules, and many-body phase for the atom. They should be related by this because this is a nonlinear process of phase. There's a phase doubling. Okay. All right. So last, I'd like to kind of say my group member is my former student Zhen Dongzhang and also now Su Nagata. Okay, working on this the molecule experiment. Okay. And also the other student working there, another experiment working on lithium cesium mixture. Okay, we have also recent paper talking about this kind of this new phase of this lithium cesium mixture near the phase bar resonance. Okay, which briefly just show some slide lithium cesium mixture. Okay, and also last experiment will develop a new type of quantum simulation machine with what we call quantum mental synthesizer. If you have any question, I'm happy to discuss during my stay. Okay, all right. Let me come back to the conclusion. Okay, thank you.
Thank you. Thank you very much. You have now time for questions, yes?
Go
ahead.
I was just wondering, I mean, your atom molecular Hamiltonian looks very much like second harmonic generation in quantum nonlinear optics. So you see this limit cycle steady state if you have some feeding and some decay.
Yes.
So two questions. The first thing is, how does it compare to that? And secondly, do you have any chance of looking into number fluctuations of your condensate?
Yes. Can you bring back the slide? All right. So yeah, maybe it's, the dynamics. Okay. Maybe let me see. Later, maybe the second to the last one. Oh, I see. Okay, I can change it. Okay, sorry. Okay, right. This is okay, right here. So what we see indeed this near the resonance. Okay, this oscillation we try very hard. This is the best we can only see oscillation no more than about 10%. Okay, and by this more or less consistent with kind of this simulation, it wouldn't take too long for this oscillation to damp out, and this also. In our experiment, we'll see a very large fluctuation. In the beginning, our atom number kind of fluctuation only about 1-2% is very well defined. But once a molecule created, it's very large fluctuation. Okay, right. So the data what I show here, we need to do a lot of kind of averaging. Okay, in order to get this you can see right here, you can see very clearly, right here the error bar is very small. Okay. And right here the error bar is much larger, but we also, for this, we need to, every single point, you need to take about 10-20 measurements, okay, to get to this error bar. Yeah.
Okay, Andrea will be first and later.
Yes.
Just so what is the reason why these three-body processes matter? Is it similar to the three-body losses where it's energy momentum conservation, but the energy scales are different here, I guess?
Right. So that's a very good question. Why three-body kind of dominates? Okay. So my understanding is from here. If you look at the Lorentzian background, it's likely a two-body thing. Okay. Because phase bar resonance itself is symmetric. Okay. But what we see on resonance, very near resonance, that's this pink, this magenta line. Okay. this is first asymmetric, okay, and that's agree with the prediction that the three-body process, depending on whether the bound state below or above this resonance, you will have a very different result. So our understanding is that the three-body process is strongly enhanced on resonance, maybe because there are more few operators in the three-body process. So that when you have a many-body system, three-body processing can kind of can dominate over two-body process.
Thank you. Now, we can take 2 more questions, provided they are not too long. Go ahead, please.
The question is short.
Yes.
Can you use all this knowledge to design a trajectory where you will get close to 100% molecules?
No, not. We try our best results so far is about kind of a 20%, and I think there's also a reason for that. Now, I guess I didn't have time to mention this. Okay, so look at this. The system doesn't really oscillate all the way to the other side. Okay, there's those kind of effective dissipation. You see, quickly drive the system near the bottom, but near the bottom they seem to be more coherent. Okay, they oscillate for longer. Yeah, so the position of the minimum determines what's the fraction of molecule you can create.
Okay, the last but one. Go ahead.
Cheng,
Yes.
if I take your Hamiltonian in the presence of like molecular condensate,
Yes.
my intuition is, and compute Bogoliubov excitation, that I'll get imaginary frequency showing instabilities, and that will give me a time scale. Does it agree with your short time scale?
Right. A short time scale is let me see. It is getting really fast. Okay, I can show this plot again. If theoretically it should be even faster. I think here we see enhancement down to about this. Let me see. So as this right here, a near resonance. Okay, the time scale reaching down to about few tenths of microsecond. I think at that time we start to be limited by how fast we can change the magnetic field. Okay, theoretically, from our understanding, it probably can be even faster because this process, the more particle you had, the faster the process will go.
Actually, I was thinking more about the plot on the left, right? Because it looks like it's characterized by some time scale, and
right.
my guess is that it's just like way in the wrong ground state. So we have the wrong number of atoms, and usually there are collective modes which show instability,
right.
And they would give me a time scale.
Right. Okay. So our experiment, I think I agree with you. Suppose there's some kind of instability, you might expect to see population increase exponentially. Okay. We are seeing something like this as experiment. I just try to more or less, well, it looks like it's a straight line, so I try to use a straight line to determine the rate. Okay. And then this the rate is shown on the right side. Okay. And I think right here we probably are already near the resonance, we're probably limited by how fast we can change the magnetic field. And a few 10 microseconds is our current limit.
Last question? No? Sorry about that. Well, okay, let's thank the speaker once more.